Welcome to a new test and teardown video. This time it's another Philips Electronic Multimeter PM2401, and I didn't even clean it up or anything, so here you can see how stuff usually looks like when it enters my lab. So this is a very rare before picture. It is of course full of dust and stuff, and I believe this one is defective, because look at that. Oops, there's one of these repair notes. Stock number, and this is the number, right? So it's 20, yes, that is the right number. It is a multimeter serial number and all sorts of stuff. So it's been taken out of something, and there's a signature and a date. So what, 20 years ago it was, no, it's on the back. It was taken out of service because of something. It says here, let's have a look. It's outside specification in the 300 volts AC range. So that is definitely what we need to look for. So let's take this off. And I believe this one is a field effect multimeter. And every time I see one of those battery indicators, I think there's a battery tester. It can also run on AC. How is that done? Because I don't see any AC. How is that working? And then you probably what? This is not light. I had the idea this was a lamp or something, but this is fluorescence or something like that. It shines up like it's a lamp. So it's activated by my LED light here. What the heck? And this is not captured by the camera very well, but to my eyes it shines like there is no light in it. But it definitely looks like there's light. But there's response on the down. So I mean, so here's how it works. And then you push the bat, and then you are in. Look at that. Battery on new. How's that possible? This thing was put on stock 20 years ago. Oh, now I get scared about the batteries. No, please don't do this to me. So those are the, how can I miss that? Those are the classic Philips battery. So you do like that, right? And then you, oh, gross. So that's wet. Oh man. How lovely. So the idea is, I need to take these out. Oh, why don't people remove batteries? There is a bad place in hell for people who's doing this. I'm telling you, baby. Here's the fun thing. This unit was put for repair 2003, right? And if we look at the batteries, they're from December 2004. So they're nearly 20 years old, and they are definitely corroded and So I think I should take out those entire boxes and clean them. Oh no. Oh man, I believe this is not the first or the last time this unit have seen battery leaks. Oh no. And this looks like somebody tried to clean it up and then all the slime went down here, and oh my god. Oh, this is bad. Somebody was so angry about this unit. I mean, see this corner? How this looks. See, this is the good corner. And here's the bad corner, so it's completely bent in like this. And the here up here there's like a deep dent. It's actually so deep I can't pull the outer cover away because there's not a lot of clearance here. So how do I bend this back? Oh, it's the same problem here at the bottom. Look at that, it's completely bent because somebody was angry and took the word throwing out a little bit too far. How am I going to get that out of the box? Let's have a little look inside. So that will be current sense resistors. Aren't they beautiful? Yeah, that's the back side of my battery boxes. I just desoldered the wires here so I can take these out and more carefully inspect what is going on here. But so far it looks amazingly clean and beautiful. It's yeah, full of just all those resistors and capacitors and all the good stuff. And that will be, where are, yeah, okay, down here we got some transistors and also one little transistors in there. But other than that, it's really not full of a lot of electronics. It's all hidden here. Here we got all the goody amplifier board. U2. And oh, there's actually a funny thing I really want to show you. Trimmer capacitors for frequency compensation. Oh, we got a big bad boy down there. And wow, is that a power supply, a switch mode or something like that? Could be. Interesting. Maybe I should try and find the schematic. Yeah, there was a funny thing I really want to show you. Here on the front, see, this is volts, right? So that will be DC volts, but you can also click like that. Now it's AC volts, right? If you go to resistance, so whoop, you can't push AC. No way. And if you are in voltage, AC, and you want to, no, you cannot do that. So there's a lock. And if you want to go to, see, DC current, AC current, I believe that is AC or DC, obviously. Ah, so this range can be either AC or DC, right? So you can click AC, haha, now it's AC. But if I'm in this range, that is a DC only range, of course I cannot click AC. This is genius. And it works all the way. So there are some funky interlocking thingies going on here, right? And it gotta be, where's the AC? That one. Oops. No. Okay, so it's locked. How the heck is that working? But that is going back and forward, and then the AC button goes in there, and somehow that works. Magic powers. That is what it is. But it's really beautiful and compact and full of good stuff. Yeah, I can't wait to see if it actually works or if it's really true about that range. It was fairly easy to find the schematic, and this is a classic thing with the Philips. So let's look a little bit here on the schematic. I took the freedom to draw it a little bit, upscale it, and fix its problems. So now it's a little bit easier to see what we're doing. As you can see here on the entire schematic, I didn't redraw all the connections, but only the most important to understand the power supply and to get that up and running. Let's zoom in a little bit on the power supply section. And here you will see that everything is actually upside down. Don't get confused about that, but this is just how they choose to draw this schematic. So battery positive goes down. So that is a little bit annoying, all right? So the negative side of the power supply goes to the on-off switch. Okay, so after the on-off switch, we have minus 6 volts on the top of C201. And then there is this transformer and a power transistor, that is the big one on the PCB. And then there is a diode and a capacitor that stores the negative voltage that this steps up to. And then there is a resistor and a filter inductor, and then C203. And on the top of that, we got minus 12 volts. And the reason why we got minus 12 volts up there, that is because of that Zener diode on the top there. And then we have, of course, the forward voltage on TS203, the basis emitter voltage. And then we have another Zener diode on the bottom, that is 6.2 volts. So all of these things added together gives us 12 volt. And so TS203 will be turned on and off depending if the voltage is too low or too high, and then it will turn on TS203 on and off, and that will give more or less a bias to the power transistor that will then step down the input voltage, and now you have a regulated minus 12 volt. So that is really cute. Maybe we should try and do a tiny little benchmark on that supply and see how well that works. So here is a close-up of this switch mode converter here. I don't know if you can see those two germanium diodes. Damn, there's something rotten about those. I don't know exactly what is causing that. Ugh, that is some slimy stuff. Yeah, I believe that will be the two Zener diode train. And that is C201, and that's our minus 6 volt input, and that is C203. That's our regulated 12 volt, our power transistor. And that big bad boy of a power transistor, I mean, this is our input power, 0.2 watts. And I don't know, why are we using all those big power parts? So this entire converter is using 0.2 watts. And it is, I mean, you can't even have it in a hand. I mean, if this is from about 1966, I can't help being a little bit impressed. So this is the nominal voltage of 6 volts, so that will be brand new batteries. Let's just imagine they're using an external power supply and it's overvolting a little bit. So that is 7, that's 8. Let's go back to nominal. So you didn't see anything on the output. So let's pretend we have a weak battery. So that's 5, 4, 3. What? 2 volts. Okay. Oh man. So this thing can just drive the battery's completely down to dead. I mean, you could definitely run this off 1 cell lithium. You see? Because that's a normal 4 volt. And then I think that cuts off about 2 volts when they're completely empty, right? So, yeah, that is, I think that will be my trick. And yes, because what you saw on the schematic is there is no isolation from battery power to your measurement voltages and stuff. So that means when you measure mains voltages and all sorts of bad stuff, this thing is not floating, right? I'm still doing my cleanup and inspection round, and I find a lot of funny things here in this unit. I mean, look at that. See all this nasty stuff here I need to clean up and all that. It's not really looking good. And that, what is that? Somebody dropped some, but look at that. Somebody changed a transistor and forgot to cut the pins. That can't be normal. Oh yeah, by the way, the input for voltage. See, this is the voltage in, let me show you here on the front. See, this is voltage times 1 and this is voltage times 10. So that means input voltage goes through this resistor there's in here. And I think that is a 10 mega ohm resistor, and then it goes into the normal system that is about 1 mega ohm or something like that, right? And so if you input here, you don't multiply by 10, right? And then there's of course a frequency compensation where you can perfect the frequency response of this, you know, attenuator, right? So that's pretty neat. Oh, here's also a little bit of nasty leak. I need to have all this cleaned, because otherwise it will of course not be accurate. And this is what happens when you go into the higher voltage ranges, and that is exactly what they said was the problem, remember? Then you attenuate via higher and higher resistor values, and that means impedances on all this input stuff here gets higher and higher. And then see, we got, for example, shielding tracks like that one here, right? That should prevent leakage from interfering with our measurements. But that is not going to help us a lot if everything is full of a layer of conductive goobity-goop. So yeah, I need to clean all that, and then you're probably gonna see that it will measure quite alright again. So I am done with all the cleanup. I think that is good enough. I've been around all the transistors and all the stuff. I think you should be able to see there's a big difference. And now I'll put back the power supply here. Oh, that is quite stuck. So I've been around this board with cleaning as well. I also saw some splat, some funny fungus kind of stuff, and that will be all the resistors for all the different voltage ranges. And of course you can see 100 mega ohms and stuff like that, right? And even 110k and so on. All the resistors to the left, I don't care at all about those, but that one to the right is definitely my concern. And we also got a lot of resistors down here for all the different ranges as well. And as you can see, they're a little bit dirty as well. But there is no way I can go around and clean everything here. And I feel that I'm probably going to go and test it now and see where are we. And by the way, those Elmas switches, oh man, that is some nice. There's just the most beautiful click feel. And you can see the first one here is only 1, and the back, that's a double. There's a very, very good feeling. Super accurate. The contacts here, right? So that's probably going to work. Let's perform a little bit of testing. So that will be DC mode. And I've selected 3 volts full range. So that will be that scale. I don't know if you can see, this is 2.5 volts, right? Yeah, I think that is what I got here for my little test setup. And there's actually a few things that I really like about those old Philips multimeters, and they all do this, and they all got this little plus minus readout meter here. I don't know how easy it is to see the tiny little red. Let me turn on. That did not help. Sorry about that. So if I remove the input, it goes back into the middle, right? So of course I got a positive into my ×1, and then it goes positive the meter. All right. See what happens if I take my DC voltage and flip it. So now it is negative. Look at that. We still get, of course, exactly 2.5 volt. And now the meter shows negative. I mean, you gotta love this. And it's all done automatically. So how the heck is that possible? I will be happy to show you why. If we look at the block diagram, they of course put this into the manual, and here you see first to the upper left, we got all the different switches and attenuators and all that kind of stuff that that puts our input into a chopper, and the chopper is in the middle of the picture. So the chopper works this way. There is a multi-vibrator that generate a signal, and then this chopper selects the input signal, positive, negative, right? So the more DC voltage you input, then you get more and more amplitude, but you get it in phase or out of phase, depending if it is positive or negative. And that is how it is able to detect the polarity of the input and just fix it so that it will show exactly the same value on your meter, because the meter shown the amplitude of the AC. I mean, it is super smart. And the cool thing about doing everything in AC, then, well, yeah, it works, of course, with AC as well as DC, more or less the same way. It's just amazingly smart. If we look at the specifications, I'm so sorry, mine is here in Dutch, but that's the only thing that I could find today. It says that the maximum input voltage is 300 volts in the ×1. So if you go up to the 300 volts, of course you can give it 300 volts. But if you take the ×10, and then you are in the in 100 volts ×10, it looks like you could potentially give it 1000 volt full scale readout, but you're only allowed to give it 700 volts in that mode. So that's just important to remember when you fire this up. Don't give it that much as you would probably do. I was actually just about to start some high voltage experiments, and of course I saw this 300 volts at full range and then ×10, so that makes it 3000. That's quite cool, but that is not allowed, of course. I actually wanted to wrap this video up because it's already way too long, so let's just say that we have been here and this is up and running. I'm not going to play so much with the AC volts, and especially not high AC volts. Not right now, at least. So that is like that, right? So that is 3 amp, and that is the 3 amp. If I want to go 10 amps, then I just select that input. I don't think it matters. Let's try and give it. See? Oh, that's annoying. How do we fix that? Those annoying smart power supplies, they go like beep, beep, beep. See? And then, yeah, see? Exactly. So when you use this input, it kind of go on the back of that switch. So if you are now in 3 amps and this is a half an amp here, and that is 1 amp full, and that is 0.5 amps. So it's also working there, and of course this is like that. Oh, that's me who's dumb. Of course I can go negative like that, right? Negative, positive. Ha! I totally love it. Anyway, thank you very much for watching. I hope you had a little bit of fun. I was actually quite happy about this meter, and at the moment I power it, oops, from a single cell lithium. So I think that is what I will do. I will just add a little cell here on the back. That's yeah, that's better than this junk that is definitely never gonna work, and it's never ever going to make me happy. No, not a good idea. That's not the way.